Hello, we will start today with chapter R, section R.2 of your textbook, set of numbers. And if you want, this is page 5 of your textbook. There are several sets where you can classify the numbers that are going to work in math. And let's start with the easiest one, which is the natural numbers. Natural numbers, they go start from 1 and go like 1, 2, 3, 4, all the way to infinity. And the natural numbers actually were the first that were invented to represent quantities. And it's pretty simple because we use this to define quantities like 1 apple, 2 oranges, 3 bananas, and goes on. And years after the invention of the natural numbers, several years, they invented a new number, which is the zero. Zero is actually invented way after the natural numbers. And then we have the set of whole numbers. And the whole numbers, the only difference is because the whole numbers include number 0. All right, after that, years later, they invented the notion, they kind of created the notion of negative and positive numbers. Negative and positive numbers. Natural numbers and whole numbers, they didn't have any kind of sign. And then we have now the integers. And the integers are, you have the negative numbers, -1, -2, -3, and on. 0 is nor negative, or is neither negative or positive. And positive numbers, 1, 2, 3, 4, and on. All right, these are simple sets. It's easy to understand. And now let's introduce you to the set of rational numbers. Now it's a little bit more complicated because rational numbers are represented by a fraction, by a ratio, like numerator over denominator. And the numerator is an integer and the denominator is an integer, right? This is to represent fractions, right? And this is kind of a way of representing like half an apple, quantities that are not a whole thing. 3 oranges and a quarter, something like that. And the next one, irrational numbers, is a subset. All these numbers, the whole thing is the set of real numbers. And irrational numbers is actually a subset, is a part of the real numbers that cannot be written as a ratio, cannot be written as a numerator over a denominator. And we will understand it a little bit later. So this is a diagram of what we talked about. We have the whole thing, the whole universe of real numbers, and inside this real numbers, then we have in one side, one part is the rational numbers, and another part is the irrational number. So if a number is rational, it's not irrational. If a number is irrational, it's not going to be rational. But inside the rational numbers, you're going to have the integers, and inside the integers, the whole numbers. And if you remove the 0, then you have the natural numbers. Let's see some examples here. And the example asks you to show that each number is a rational number by finding 2 integers whose ratio equals the given number. And the first one is easy, is already represented by a ratio, right? If you have -4 over 7, or if you have 4 over -7, or even if you have, let's say, 8 over -14, or something like that, then you have -4/7. This is a rational number. And the next one, 8. Can you represent 8 using a ratio? Well, actually, yes. 8/1 is a ratio, or 16/2, 32/4, 24/3. All these are ways of representing 8 using ratio. Okay? Letter C. So this is okay. Rational number. This is okay. Rational number. Let's see this. 0.6. But notice there's a line here on top of 6. That means these numbers repeats itself all the way to infinity. Is 0.6666666 and on. When you have a repeating decimal number like this, you can actually represent as a fraction, and this is going to be 2/3. So this, yes, we can represent as a rational number. And letter D, we have 0.87. So 0.87. Can you represent it as a fraction? Well, the easiest way is 87/100. And okay, yes, it is a rational number. So we proved that all 4 options are rational numbers by finding 2 integers, at least 2 integers whose ratio equals the given number. Another example here, check the set to which each number belongs. And let's see the first one. And it can belong to more than one set. The first is going to be, let's use this. Number 6 is a natural number. No, because it's a negative, so it's also not a whole number. But yes, it is an integer, and we can represent as a ratio. It's not an irrational number, and I can say all these numbers are real numbers. All these numbers are real numbers. Square root of 23 is not a natural number, not a whole number. If you try square root of 23 on your calculator, you're going to see it's not an integer. It's not actually a rational number because you cannot represent as a ratio of 2 integer, numerator and denominator integers, so you cannot represent as a ratio. And yes, the rational number. -2/7, not natural, not whole, not integer, yes, rational. Number 3, yes, a natural number, yes, a whole number, yes, an integer, yes, a rational number, not irrational. And 2.333333 all the way to infinity. Not natural number, not whole number, not integer, rational. Remember, if it's a repeating, the decimal is repeating, yes, you can represent as a rational number and not irrational. Great, now skill practice. Now you try by yourselves. Pause the video and try this skill practice by yourselves. And after that, we will check it out. All right, now let's check. Number 1 is a natural number. Yes. yes, whole number, yes, integer, yes, rational, and is it real? All these numbers are real numbers. 0.47, not natural, not whole, not integer, but yes, we can represent as 47 over 100, for instance. Okay, not irrational. What about square root of 5? Not natural, not whole, not integer, rational? I don't think so. I cannot think about any numbers that I can put on a ratio and make a square root of 5. So it's irrational. And -1 over 2, not natural, not whole, not integer, yes, a rational number. Great, let's move on. Let's understand, just try to understand a little bit better this thing about rational numbers and the difference between rational numbers and irrational numbers. And I like to think when you have the numerator and the denominator, I like to think this as a pizza and a number of people that we can divide this pizza. So let's say pizza and people. And we have here one whole pizza that we will divide by 6. So this we can represent by the ratio 1 over 6, right? If I have 2 pizzas like that, I can give two slices of pizza to each person, 2 slices like that to each person, and so on. And if I have more people, let's say we have 1 pizza, but I have 12 people, then I need to split. I need to divide this, each slice in the middle, and then we will have, instead of 1 over 6, we will have 1 over 12. So when you think about the ratio, I think is a good way of remembering is a pizza that you will divide by a number of people. Numerator over denominator. And each slice that you divide, can divide as many times as you want. It's always going to be a rational number because you can represent it by using a ratio. Let's see this other pizza right here. You see, we have a few nice slices, like this is 1 over 6, right? 1 over 6. And this is a smaller one. We divided by in half, it becomes a 1 over 12. And this slice here, we divide by 3. So it's going to be each one 1 over 18. But what about this slice here? Can you think about a fraction that you can use to represent this? Someone got this slice and bit this slice, took off pieces, and there are some crumbs as well. This is a irrational number. Irrational number is this kind of thing that have all the crumbs and decimals and the small pieces that we cannot put together and make it represent it using a fraction. A very well-known number, which is an irrational, famous irrational number, is pi. Usually you can say pi is approximately equal to 3.14, but pi actually is an irrational number. It goes like 3.14, 15, 92, 65, 35, and on, all the way to infinity. It's a very famous irrational number. Okay, this concludes our lecture today, and now we have an activity. You go to Teams, Microsoft Teams, and open this activity classifying numbers by sets, and do it by yourselves and using the link on Teams to Microsoft Forms.